Hello. So I'm going to try to explain this problem, house robber, and let's before explaining, let's just read the three problems which are there in LeetCode. All of them are pretty related, so we'll try to solve the first one first because that's the easiest, and then we'll go on to the other ones. So basically, you're a professional robber planning to rob houses along a street. Each house has a certain amount of money stashed. The only constraint stopping you from robbing each of them is that adjacent houses have security systems connected and it'll automatically contact the police if adjacent houses were broken into on the same night. Given an integer array nums representing the amount of money in each house, return the maximum amount of money you can rob tonight without alerting the police. Okay. So let me just explain the situation here. You have that better. Okay. You have a row of houses like so, and you want the max value that you can rob. You want the max value that you can rob, provided you do not rob adjacent houses. So you can rob this one, and then you can rob this one, or you can rob this one, and then you can rob this one, and then you can rob this one. So basically, you can rob, but you can't rob this one. If you decide to rob this one, you cannot rob this one. That's the whole problem. You're supposed to return the max value. Let's just do a crude example to see the problems naive approaches could have. So let's say this has value 1, 2, 3, and 4. So if I rob this one, and I rob this one, and then I rob this one, and then I rob this one, the total I'm going to get is 5 plus 5, that's 10. But is that the best? No, of course, it doesn't have to be, because let's say there is 1,000 here. So after this, you wouldn't want to rob this one, you'd want to go to this one. And maybe there's 100 here, so then you'll want to rob this one. So this would be what you want. Let's say this is 0. So that's what you want, right? You don't want to be robbing. You want to rob this and this for sure, because that's what's going to give you the max value. So you need to make sure that you don't rob this, or this. And then the next option is between these two. And then you can choose one because 0 is lesser than 1. So we can see that quite obviously you don't go like 1, 3, 5, 7. You don't do that. So what we could do in such a problem is recursion, and we'll come to that. We'll come to that quickly. I think we'll also read the other problems, and then it'll be very easy to solve these two once you understand the first one. This is the same problem basically. I'm not going to read through it again, but the only difference is that the houses are in a circle, and this is also a pretty related problem, except that the houses are in the form of a binary tree. So once you can solve this, it's kind of trivial. The other two, not completely trivial, but yeah, it's pretty easy. So let's see what we could use as an approach for this one. So like I already said, you can use recursion because that's the most intuitive way. This is a dynamic programming question, by the way, and we'll be reaching there. But for me, because I just recently learned dynamic programming, for me it's always easier to think of a recursive solution before I try dynamic programming, because once you know the intuition, like how the flow goes, okay, that was a bad example. But once you know how the flow goes, then to convert that to an iterative dynamic programming solution is easier than if you just try, at least for me, if I just go try dynamic programming directly. So let's look at it in a very intuitive way, and we'll slowly build up. So when you see this problem, what would you think? You want the best possible route. So you need to find the best possible route, right? You need to find the best possible route. Like you stand at a house and then you toss the coin, and then if the coin shows heads, you loot the house. No, that's not how it works. At least you won't get the max value that way. So you want to find the best route. And how can you do that? So what would you do? You'll say, I'm at house 0. Okay. So then let's say there are 5 houses. Let's say there are 4 houses. So at house 0, what I could do is I can say, hey, I'm going to loot house 0 for sure. So now the next house I can loot is 2. But if I decide I'm not going to loot house 0, then the next house I should loot is 1. And I'll explain in a few minutes what I really found tough to understand about this question. But before that, let's just go through the entire tree. So then I said there are 5 houses. So you have 0, 1, 2, 3, and 4, right? So 2, and then you can come to 4. And or you could, so if this is yes, if this is no, you come to 3. If this is yes, then that's all. Like there's nothing more you could drop, because you do 0 to, yeah, you don't drop 0. You drop 0 and then you directly drop 3. Then there's nothing else you could drop. Or you could decide not to drop 3, and then you could drop 4 instead. So you robbed 0, and then you robbed 4. Or you could actually decide not to rob 4. But yeah, why would you do that? So yes or no. From no, you're going to get nothing, and from yes, you're going to get nothing. But you can add the value of 4 in this, right? So let's say plus 4. Plus 4 is the value of 4, okay? Not actually plus 4, of course. And this is just going to return its value, so that's going to be plus 4. And this one is going to be plus the value of 3, right? So because this is going to just return 0. Plus 4 is from this, okay? And then this is going to do this plus 3, which is just 3, I mean the value of 3. And then and then you take the bigger one, of course. So you say, if I come to 3, then I'm not going to loot 3, I'm going to loot 4. Okay, for now, let's just say they have the value equal to their index. It's easier to think of. So I say, okay, fine, I'll rob 4. So then if I come to 3, then I'm going to rob 4. I'm not going to rob 3. So I return back saying, hey, it's going to give me 4. But then if I come from here, I'm saying I'm going to give you 4 from here plus 2, because I decided to rob 2, right? So this is plus 4 plus 2. This is 6. Obviously, you would go with 6. And over here, you can add the value of 0 as well, but it's 0 here, so it doesn't make a big difference. Or let's just say it's 10, because 0 is a very sad value. So so then you have 6 plus 10, that's 16, because I took this, not this. So if I come to 2, I'm going to rob 4 directly. I'm not going to not rob 2 and then go to 3, because I'm robbing 4 eventually. And then I come with 16. And then if I go to 1, okay, let me just another color. If I go to 1, then I could do yes or no. If I say yes, then I have to go 3 next. If I say no, I go to 2 next. And what you can see, like almost immediately, is that I already did all the work. Okay, I already did all the work for this. If I come to 3, then I know what I want to do. So I already did it. So then you can just draw it again, like if you really need it. And then no, if it's no, then I take 2, right? And 2 is this whole tree. So I know that if I go to 2, then I'm going to say yes. Okay, let me just draw it for the sake of it. Yes, no, I go to 4, 3. Yes, nothing. No, I go to 4. Yes, no. Okay. And this I already did. Now 3. If I say yes, nothing. And if I say 4, sorry, this is 4. Yes, no. And this is nothing, and yeah, so on. You can fill in the values. So there's a lot of repeated calls. If I do this, if I come, see, I called 2 here, then I called 2 here again, I called 3 here, and I called 3 here, I called 4 a billion times, I called 3 over here as well, I called 4 here again, I called 4 here again. So there's a lot of repeated calls, and you don't want repeated calls. Why do repeated work, right? So this is where we think of the dynamic programming. What could you possibly do, right? Some things you could do are you could store the value. So once I come to 2, I check if I already have the answer for 2. So this is called memorization, right? Memorization is just memorizing whatever values you got. I mean, not actually memorizing, but putting them in an array. So if I come to 2, I remember what values I got at 2. So when I come here again, I say, hey, I already did the value for 2, and then just directly give the answer for 2 back. And here I give the answer for 3 plus the value of 1 and go back. So then I have done the value work for 1, right? So that's memorization. And I'm not going to go through the entire step of memorization because it's pretty intuitive. It's the same recursive structure, but instead of when you come to a particular node, you're going to check if you already have that value. Okay. So let's go and try to make this iterative. What is iterative? That's what dynamic programming is. So this is a recursive solution. This is also recursive, but smart recursion. Okay, what can we do about dynamic programming? So what I could think of doing is, I come to, we know what he's doing. So okay, let me just first discuss something. Then we need to know how many unique function calls are there, and that's what we're going to use as a space complexity for dynamic programming. At least in the starting, we'll optimize it later. So what is space complexity here? I mean, what am I saying? What is the number of unique calls? So if I have 5 houses, then I could have 5 unique calls because each call is defined, excuse me, each call is defined by this number, right? I'm calling 2. There's no other information that I'm giving it. I'm just calling 2. So there are 5 unique calls that I could possibly make. So I'm just going to use something which is going to be 5, 1, 2, 3, 4, 5. So I'm going to show you how to do dynamic programming on this. So what I could do is, yeah, so something which I really struggled in this particular question was that, and I'm pretty sure at least some of you, if you're average like me, would feel that if I say no, okay, if I'm saying no at 0, then I have to make sure, I have to absolutely make sure that 1 is looted. Because what's the point if I say no at 0 and then I say no at 1, then I'm looting 2. But I could have just gone from 0 to 2 directly. So I had to make sure that 1 is, if I call something with a no, then I have to make sure that it's looted. So I'm basically saying I'm passing 2 parameters into the function. Okay. But is that required? Like if I come to 1 and say, hey, you have to be looted, you cannot say no to yourself, then first of all, the number of unique calls is increasing because I'm now passing each call with 2 parameters. And it's not even required because let's say, for example, that I come to 1 and I say no to 1. So I go to 2. Okay. If I go to 2, then the value I'm going to return is, let's say, v2. Okay. For now, v2. And because this was a no, I just returned, and yeah, let's say I said no at 1, right? So then I get, and let's assume that it was, I said no at 1 because this was lesser than what I could have got from here. So then this would go as v2. But what would this be? This would also return v2, right? This would return v2. And what would the value reaching here be? v2 plus the value of 0, which is obviously going to be greater than v2 because I'm assuming that values are going to be positive. So quite obviously, I don't have to tell 1 to loot itself because whatever happens, I'm going to get that result anyway. So that's going to like be a self check. If I say no to 1, then by default, I'm going to say yes to the next one because I'm going to say, if I say no and come to 1, then I'm going to say yes and go forward because if I say no, then I would have got the right answer from here anyway, a better answer from here anyway. So you don't have to worry about sending that parameter, that no extra no parameter. That was something I really struggled with in the starting when I was trying to understand this problem. So you're going to try to understand the problem in this way. So basically, if I'm at the ith house, the way I would decide what houses to loot is that I would say, let's say f of I is the function which gives you the max value from in onwards. Okay, so if I'm at the ith house, then I would just check if val of I, or the value of the ith house, plus f of I plus 2 is greater than f of I plus 1, right? And then if it's greater, then I would say, hey, f of I is equal to val of I plus f of I plus 2. Otherwise, I would just say f of I plus 1. So this f of I, which I'm writing, is what we're going to store in an array. So we're going to say dp of I, okay? And but this wouldn't be valid for something which is greater than the size of this. So then if I'm at the last element, then these last two elements would be something which we have to take care of, because we obviously can't go further from them, right? That would be going out of bounds. Anyway, so f of I is going to be equal to deciding how many, whether I should not loot this house, or should I loot this house. If I loot this house, should I go there? I have to go there. And if I don't loot this house, then I just have to go here. So that's basically the crux of this idea. And what you're going to do is you're going to say, put another color. You're going to say, hey, dp of I, right, is equal to max of val of I plus dp of I plus 2. I'm calling, okay, by the way, I'm calling this dp is because it's just dynamic programming. There is no other, I could have named the array better, like max values or something, but that's okay. So and dp of I plus 1. Okay, so actually, when do the houses that are going to get robbed get fixed, right? So when let's do a dry run and see like the properties of what's happening, so that we get a feel for, like, we got a feel through the tree. Let's try to see what happens when you do a dry run. So I hope all of you understand this thing. It's basically either I put this house and go to the I plus 2th house, or go to the I plus 1 house. So we want to check, like what we did before, if I come here and I say no, if this house was a no and I just directly did this one, I want to make sure that this house says no as well. Okay, we want to check if that's actually happening, right? Because if this one if this one said no, there's no sense for sorry, if this one said no to itself, like the robber came here and decided he's not going to loot this house because it was better to loot this one, right? This one and onwards. Then I had to make sure that this one is a yes, because at least from here, if I start from here, it doesn't make sense to say no here and go to this one if this one also said no and went to this one, right? I hope that's not confusing. At least from here onwards, this should be a yes. So let's see if that's what happens. I don't know what this was for. Okay, so let's do like a random array dry run to see if it's actually working. Then we'll see if we can further improvise what we did. So this is the array, and let's say this is 500. This is like a super wealthy guy, 2000, and this is 3, and this is like 30. Okay, let's actually go a little further, because it would be easier to see the patterns of what's happening. We'll also keep a track of what houses he's looting, right? So that would be, and 500. So we decided that we are going to go from the back. So over here, it is going to be 30. And the houses that he's going to loot, let's see, this is 0, 1, 2, 3, 4, 5, 6, 7, 8. This is just going to be 8. If he has to make a decision at 7, then what would he do? Would he loot 7, or would he just go to 8? obviously he'd go to 8, right? So he would get, because he would get 30 then. That would be just 8. Okay, this came to what we wanted to check before. We want to make sure that this one, when he comes here, given all the decisions he made earlier, he says yes to this. So then this one's list of looted houses should contain 6. Let's see if that's what happens. So it could be either 2030 or just 30, right? Val of I plus val of I plus 2, or just val of I plus 1. Of course, he's going to go for 2030. So that matches our expectations. Cool. 6, 8. What about if he comes to 100? So he could either get 100 plus what he would get here, that is 30, right? So 100 plus 30, or he could get 2030. And obviously he would go for 2030. So that's 6, 8. Okay. And also something that we can notice, if he comes to house and says no, right, then for sure in the future these houses are going to stick with him. Like, he's going to rob these houses for sure. And we'll see. Actually, why that happens is because in any future list of houses, either this or this is going to be included. Right? Any of these have to be included. And since both of them are the same, both of them will be included. Both meaning 6 and 8. So let's come to 5. So either he gets 5 plus 2030 or just 2030. So that becomes 2035. So that matches what we expected, right? We said if he says no here, then he has to say yes here, because it doesn't make sense to say no here and no here at the same time, right? So this becomes 4, 6, 8, right? Then we come to this one. So he can say either 10 plus 2030 or just 2035. And he would obviously go for 10 plus 2030. So that becomes 2040. And this would become 3, 6, 8. So even though he didn't say no here, this got rejected in the next one. So let's see what happens in the coming one, right? So he can either say 100 plus 2035 or just 2040. But he would go for 100 plus 2035. So that's what 2135. That's 2, 4, 6, 8. So since whatever is the same in these two will continue for sure, okay? So we don't know if 3 or 2 or 4 are going to be constant, or in the final list at least. So he comes to 40. He can either get 40 plus 2040, that's 2080, or 2135, and he would go for 2135. So now it's 2, 4, 6, 8, and those 4 are finalized. Like, these will be in the final list. He comes to 500, and he can either decide for 500 plus 2135 or just 2135, and of course he's going to go for 500 plus 2135, which is going to be 2635. So he's going to load this one, 0, 2, 4, 6, 8. And I hope this makes sense, because this is a very clear dry run. And at least when I've been learning dynamic programming for like 2 weeks now. And this is what really helps me. I find it, like I already told, I find it difficult to think of a dynamic programming approach directly. So thinking of how the flow goes really helps me. Now the next question that we can do is, a question which we can ask in a lot of dynamic programming problems is, am I using the complete, like I'm coming from the back, I'm filling, am I using the complete thing, or am I just using a fixed limit, right? So let's see if that's the case. At any block, I am only using dp of I plus 1 and dp of I plus 2, right? I'm not going to be using anything further than that. So at 500, I'm just going to be using dp of 1 and dp of 2. So do I need to store all of them? Like, I'm not going to use them. Why am I storing all of them? That's a very bad idea, right? So what I could do is just save these two values. As I go on, I just save this, and then I keep updating it. So if I call this A and I call this B, then I keep updating it, right? So I could say, hey, so this is A and B are the same here. So now A next goes to this and B comes to this and goes on. And the final return value will be B. And because this is symmetric, like who said that this has to be the last house? This could be as well the first house, right? So because it's symmetric, we can also come from this direction. I mean, sorry, like assuming we could also come from this direction is what I meant. We already came from that direction, but we could go from this direction as well. And for me, it was easier because this one is directly like going in the direction that we did the dry run in. That one is actually easier to think because that's so close to the recursive tree approach. But if you notice the battery of the problem, you could do the exact same thing the other way. So let's try to do that. So basically, what you would do is you would say, hey, A is equal to 0, B is equal to 0. Okay. And why I'm doing this, instead of saying A is equal to nums of 0 and B is equal to nums of 1. So the A is the father house, okay, and B is just the previous house. Why I'm doing that is because in case there's a problem in which these could be negative values, it would be, if all of them are negative, it would be best for the thief to not take anything. Why would you steal a house which has negative value, right? You'll be losing stuff. At least that's the physical meaning of it. So that's why we take this, and then we, instead of starting from 2, we start from 0 itself, right? So let's try coding this, and let's see what happens, right? So so what you're going to say is int a equals 0, b equals 0, and what did we say? We said that we'll be going from this end, right? I'll show you how to go from that end. So at each point, basically, you'll be checking the previous two values. Is val of I plus a greater than b? Because b was this, val of I plus a. If so, then b is equal to a val of I plus a, otherwise b will be the same, right? So we don't have to update b if this is not greater. And a will have to be updated on every turn. So a will be equal to b. Okay. So what we'll do is we'll go from the starting int I equals 0 and I is less than nums size and I plus plus. Okay. And inside this, what you want to check is first we say int val, okay, is equal to nums of I plus a. That's what we did, right? We did that. And then if val is greater than b, then we say b is equal to val. Otherwise, it will remain unchanged, right? Like, let's see a case in which b remained unchanged. Here, this was a, this was b. I mean, when you're deciding for this guy, this was a and this was b, right? This was a and this was b. And because 40 plus 2040 was less than b, b remained the same, but a changed. So a has to be here and b has to be here, but b remained the same. So we don't change this thing. And since we want to keep a as the value of b before it gets changed, we change a here. Okay, a is equal to b here before it gets changed. And finally, you just return b. I think this should work. Let's see. Okay, let's see. Yeah, okay. So yeah, so it definitely works, and we showed why, and I hope you guys understood. Okay, I'll explain this as well. This is basically the same, pretty much the same thing. Okay, I'll do one thing. I'll explain. Yeah, okay, I'll explain it now. So let me just quickly go through it. This is a very trivial extension of that one. Okay. So here arranged in a circle, right? So now this first one and last one. So if they are giving it to you in an array. Ouch, that was like really bad. Let me make another attempt. Okay, this is better. So then you can't drop the first and the last house simultaneously. So what's the easiest way to do that? So when I was doing this problem for the first time, remember that problem which I told you in the starting, which I had, if I go with a no, then I have to make sure that the next one is yes. That same problem I had when I was understanding. This was the first problem I tried, and I had the problem understanding. But then it became clear that, so what I do is I compute the value for this, because I know that if I start here, right, and whether I decide to, if I decide to loot it, then I cannot decide to, I cannot loot this guy. But what I struggle with is that, what if, shouldn't I tell that this has to be looted? Like, if I'm not including that guy, then loot that for sure, right? That's the better idea. But actually, it's smarter to just, or it's actually right, to just compute the value for this and also compute the value for this, right? Okay. And if this was not looted in this one, then actually this one would have given you a better result anyway. If that had to be looted, right? That had to be looted. This would have given you a better result anyway. And it is possible that you loot this one and the second last one together. In that case, you should not loot this one, and you should not loot this one. So it's possible in some cases that none of these are looted. The first and the last one are neither looted. In that case, the answer that you get, so then we're going to compute it twice. You're going to take it as two arrays. You're going to compute it with this one, and we're also going to compute it with that one. This, okay, means draw the different color. You're going to compute it with this one. Yeah, and if it's the case that both of these are not looted, right, then both of these answers are going to be the same. And if this is looted, or in this one's like time when you are calculating it for this one, this was not looted and this was not looted, then for sure you will get a better answer when you do this. So you just take the value for both, and then you take the max value of both of them. I hope it's clear. Actually, just think about it twice and you'll be able to understand what I'm saying. So we're going to go from here to the last -1, and also from the starting till the end. And it's possible that this is looted and this is not looted in the final thing, the final list of houses. Or this is looted and this is not looted. Or it's possible that this is not looted and this is looted. In which case, this answer will be better than this one. Okay, so let's call this A and let's call this B. If A is looted and B is not looted, then the first answer will be the first answer will be greater than the second answer. If A is not looted and B is looted, then the second answer will be greater than the first one, because you're looking at only a subset, right, in the first one, but in the final one you're including the last one. And if both of them are not looted, then both their answers are going to be the same. At least that's how I think. So let's go code this. Yeah, in this particular question, there's one corner case which when I was solving for the first time that I missed. We are running the program from 0 to n-1, like size -1, and also 1 to n. Okay. But there's a particular case, so then we are saying if 0 is looted, then you should not loot the last element. But if there is only one house in the whole circle, then it's equal to the first and the last element, in which case you can loot both the first and the last elements together, right, because they're the same. So that's a corner case which you have to take care of. So we're going to take care of that first. If nums.size equals to 1, then just return nums of 0, because obviously you'd want to loot that house. Otherwise, let me just copy the code from here, because that's what's better, right? And this is B, and here again I put A equals 0, and let me put actually B2 equals 0. And my naming convention is terrible, I agree. I'm not great at naming. This is 1 and this is num size is going to be -1, like we already discussed. And this is going to be equal to b2, this is going to be equal to b2, this is going to be equal to b2, and I think we're done. Finally, you just had to return max of b comma b2. Let me see. Okay, let's see if that works. Yeah, okay, it works. And yeah, pretty much it. Now I'll just go over this last one. And I know it's already really long. It's my first video. So this last one is the binary tree one. So these houses are arranged in a binary tree. So he can't attack a parent and a child together. He can attack both the children separately. I mean, both of the children together. But if he's attacking the parent, then he can't attack the child. Or it's called directly linked or whatever. And it is possible that it doesn't have both children, of course. So let's say it's something like this. So if he's attacking, a possible situation would be he attacks this one, then he cannot attack either of them. Let's say he wants to attack this one, so then he would attack that, and he's allowed to attack this one. Let's say he attacks this one, then he can't attack any of these. So this is a possible situation, and it is also possible in the same case that he doesn't attack the root, he attacks this, and he cannot attack any of their children then, so then he attacks this and he attacks both of them. He can do that. So basically we have to, same logic, just keep a track of what the previous, if I attack the parent, then I have to take the sum of attacks of all what I would have done if I was making the decision at the child of these. Okay, so basically if I attack I have a decision to make here, and the decision is each of these children are going to give me the values if at them and the value at the children, like how we decided, right? Which can be same. Okay, so they would give this value, the value at this, and the value at this is what we required. Here this is going to be the value at the child node, and this is going to be the value at the grandchild node. And if he hits null, then it's obviously going to be 0, 0, because he cannot do anything, right? So then that's what we had in the starting, a equals 0, b is equal to 0. That's going to be implemented at the null here, because the child of last one is going to be 0, and the grandchild of it is also going to be 0 because it doesn't exist, right? So let's do that. So then for this one, because we have traversed the tree, what we'll be doing is we'll be sending back. So then we'll have to send back something. It's not like A and B, it's an iterative thing. So when we are sending back, we're going to send a pair. We're going to send a pair of the decision at the child and the decision at the grandchild. So over here, let me write another function. It's going to be pair int. That's going to be the return type, and I'm going to call it loop because of lack of a better choice of words. And I'm going to put the tree node there, and this is going to say if root is equal to null, because take care of the base case first and any recursive solution. If root is equal to null, what you want to do? You want to return make pair 0, 0, right? And finish that. Else we say is going to be loot the left child, so that's root, and I'm not going to check. Yeah, I'm not going to check whether it exists, because I know the null will be taken care of when I go down, so it's okay. All of these are terrible naming conventions, but yeah. Okay. So now what is val here? Like what we did before, val is going to be equal to small, we want, what is val? Root, oh, let me not call this, let me call this value actually. Otherwise you get confused with val. Okay, so root val, right? Because that's value, nums of I, plus the value at the grandchildren, right? So small answer left dot, yeah, their grandchildren. So second plus small answer right dot second. And okay, or yeah, earlier when I wrote this, I would actually call this loot root. That would make more sense. If I loot the root, then this would be the case. If I don't loot the root, no loot root, then I would just return small answer left dot first plus small answer right dot first. And what am I going to return? I'm going to return make pair. The first one is going to be the max of both of them, right? The decision I'm going to have over here is that, right? So the first one is going to be max of loot root and no loot root, comma, what would be the grandchild for the previous one is the child over here. So what I'd give here is no loot root. And over here what I'm just going to do is say, hey, if yeah, auto answer is going to be equal to loot the root, and the final answer is going to be return max of answer dot first, because the decision I make at the parent, or answer dot second, because if I decide to loot the children, what would happen, right? Yeah, so actually, do I need to take, I think I don't even need to take the marks of that. I just need to take the answer first, because this is going to give me the marks of that anyway, right? So let's just see. I think it will always be the case that, let's see if it works. Yep, and it works. Yeah. So yeah, and I hope you guys understood what I was trying to explain. Thank you.